Each new image from the James Webb Space Telescope represents a groundbreaking revelation, offering humanity a fresh perspective on the universe we've never seen before. Today marks an exciting chapter in our exploration of the cosmos, as we delve into the astonishing advancements made possible by this marvel of human engineering. The more deeply we observe the universe, the more mysterious it becomes, a sentiment that perfectly encapsulates the journey of cosmology, especially in the age of James Webb. With the beginning of a new era in astronomy, the world is now witnessing the full capabilities of the James Webb Space Telescope, a project more than 2 decades in the making. NASA launched this $10 billion telescope with the ambitious goal of capturing starlight from the earliest galaxies formed in the aftermath of the Big Bang. Despite various delays, the telescope has now begun delivering unprecedented results, and its latest images are sending shockwaves through the scientific community. These revelations challenge our entire understanding of the universe, compelling us to rethink everything we thought we knew about its origins. The most recent pictures from the Webb telescope hint at the existence of another universe at the very edge of our observable universe. This discovery could potentially force a complete revision of our textbooks on the universe's beginnings. For decades, the widely accepted view of the universe has been that about 13.8 billion years ago, the Big Bang occurred. In the seconds that followed, the laws of physics as we understand them ceased to apply. Everything that would eventually become matter exploded into existence, with particles like electrons, photons, neutrons, and protons emerging in the blink of an eye. These building blocks would later give rise to stars, planets, and galaxies, all expanding outwards in a smooth, near-perfect manner on a cosmic scale. In cosmology, smooth refers to the even distribution of matter across the universe. If you were to draw a shape around any region of the universe, the matter inside it would be nearly as evenly distributed as in any other region, at least on a large scale. On a smaller scale, such as between galaxies or within a galaxy cluster, matter becomes unevenly concentrated, creating dense clusters of galaxies. Scientists also speculated that shortly after the Big Bang, a process known as inflation occurred, rapidly expanding the universe from a tiny point. This inflation continues to influence the expansion of the universe to this day. This concept of a lambda cold dark matter, LCDM, model represents the standard view of the universe's evolution. In this model, the universe's expansion is depicted like an ever-widening funnel, with matter spreading out over time. However, alternative theories have also emerged, prompted by data from astronomical observations. One of the most important pieces of observable data that supports these models is the cosmic microwave background, CMB, which is essentially a faint radiation left over from the universe's infancy. Scientists can detect this radiation using radio telescopes, translating it into an image that provides a snapshot of the universe about 400,000 years after the Big Bang. This image reveals how the universe was distributed before stars, planets, and galaxies formed, a time when everything was packed much closer together, with only minor fluctuations in density that would later develop into the structures we observe today. The CMB serves as compelling evidence that the universe began in a hot, dense state and has since cooled over time. The ongoing expansion of the universe can also be measured, allowing scientists to track the rate of this expansion. As we observe galaxies that are far off in the distance, we are essentially looking back in time, witnessing the universe in its earlier stages. To study the universe's earliest formations, astronomers first relied on the Hubble Space Telescope, which, in 1995, took images of a seemingly empty patch of space in the Great Scoop region. Over 10 days, Hubble revealed thousands of galaxies at various stages of formation, surprising scientists with the amount of hidden cosmic activity. By 2016, Hubble had discovered the most distant galaxy known at the time, named GNZ11, located 400 million years after the Big Bang. Despite its significance, GNZ11 was relatively small compared to the Milky Way and did not raise doubts about the LCDM model. However, the arrival of the James Webb Space Telescope has dramatically shifted our understanding of the universe's formation. Launched in 2022, this $10 billion telescope has delivered results that suggest galaxies formed much earlier after the Big Bang than previously thought. And some of these galaxies are unexpectedly massive, brimming with stars. These discoveries have shaken the academic community, as they challenge the prevailing theories of galaxy formation. Some of the most distant and largest galaxies observed by Webb appear to have formed just 350 to 500 million years after the Big Bang, defying expectations and suggesting that the early universe was more active and complex than the current models predicted. One of these galaxies is even believed to be more massive than the Milky Way, which raises questions about how galaxies could grow so large so quickly. If these findings are accurate, they could signal the need for a major revision of our understanding of the universe's evolution, potentially indicating that the universe expanded much faster than we initially thought. This would require new theories and possibly even new particles and forces to explain how early galaxies formed so rapidly. In summary, the latest discoveries made by the James Webb Space Telescope have opened a new chapter in cosmology, forcing us to reconsider everything we thought we knew about the universe's origins and growth. What we once considered settled science is now being re-examined in light of these groundbreaking revelations, pushing the boundaries of our knowledge and reshaping the very foundation of astronomy. The structure of dark matter halos remains a debated topic in cosmology, particularly when considering the cusp versus core issue in their density profiles. Simulations typically predict a cuspy central density for dark matter halos, but observations of dwarf galaxies and other structures suggest a more core-like profile. This discrepancy raises questions about the role of processes such as supernovae and black hole growth, which are not fully understood or incorporated into current simulations. Additionally, a significant challenge lies in the tension within Hubble constant measurements. Recent measurements of the Hubble constant, which defines the rate of expansion of the universe, have revealed a persistent disagreement between values derived from local observations, such as Cepheid variables, and those inferred from the cosmic microwave background (CMB) by the Planck satellite. This tension suggests potential flaws in our cosmological models, like the lambda CDM model, or it may point to systematic errors in the measurement techniques that need further resolution. Beyond these specific challenges, the lambda CDM model itself leaves some fundamental questions unresolved, particularly regarding the nature of inflation. The model, while robust in many respects, is still subject to ongoing scrutiny from both observational data and theoretical inconsistencies. One of the biggest mysteries in modern cosmology revolves around dark matter. This elusive substance, which is inferred from its gravitational effects on visible matter and the cosmic microwave background, makes up roughly 85% of the universe's total matter. Despite decades of research and numerous experiments, the particles that constitute dark matter remain unidentified. Understanding dark matter is not only crucial for solving a fundamental puzzle in physics but also for understanding the evolution of the universe and its large-scale structure. The discrepancy between simulated predictions and observational data on the distribution of dark matter halos, especially the cusp versus core issue, highlights the complexity of the problem. While simulations predict cuspy dark matter distributions at the centers of galaxies, observations suggest a more spread-out, core-like distribution, particularly in smaller dwarf galaxies. Additionally, the missing satellite problem persists, where simulations tend to overpredict the number of small satellite galaxies surrounding larger ones, such as the Milky Way. This gap raises questions about the interaction between dark matter and baryonic matter, normal matter such as stars, gas, and dust, and how baryonic physics influences the formation and evolution of dark matter structures. Understanding how baryonic physics affects dark matter is essential for refining our cosmological models. Another significant challenge comes from measurements of the Hubble constant, which describes the rate of expansion of the universe. Different methods of measuring the Hubble constant have produced conflicting results. Local measurements using objects like Cepheid variables yield higher values for the Hubble constant than those inferred from the cosmic microwave background by missions like the Planck satellite. This discrepancy suggests that either there are issues with our cosmological models or systematic errors in the measurement techniques that have yet to be addressed. In addition to these observational challenges, the lambda CDM model faces theoretical issues, particularly regarding the cosmological constant, lambda, which is used to explain the accelerated expansion of the universe. Quantum field theory predicts a much larger value for lambda than what observations suggest, creating a significant puzzle for physicists. This discrepancy highlights our incomplete understanding of dark energy, the mysterious force responsible for the accelerated expansion of the universe. Moreover, while the lambda CDM model is successful in predicting the large-scale structure of the universe, it has limitations when it comes to smaller scales. Understanding galaxy formation and evolution requires a more nuanced approach that incorporates both dark matter dynamics and the complex processes of star formation and feedback mechanisms. The launch of the James Webb Space Telescope, JWST, marks a significant milestone in cosmic research. Building on the legacy of the Hubble Space Telescope, JWST's advanced capabilities enable astronomers to look deeper into space and further back in time than ever before. By observing the faint light from distant galaxies, JWST promises to unravel the mysteries of galaxy formation and evolution in the early universe. Early observations from JWST have already challenged existing theories of galaxy formation, with the discovery of massive galaxies dating back only a few 100 million years after the Big Bang suggesting a much earlier start to galaxy formation than previously thought. These discoveries raise important questions about the conditions in the early universe and the processes that facilitated rapid star formation in these ancient galaxies. Additionally, JWST's observations provide crucial insights into the evolution of galaxies over cosmic time. By studying the diversity of galaxies at various redshifts, astronomers can track the development of their structures, star formation activity, and chemical composition. These observations will help refine models of galaxy evolution and improve our understanding of how galaxies like the Milky Way have evolved over billions of years. Beyond galaxy formation, JWST's observations also contribute to our understanding of the cosmic microwave background, CMB. By studying the faint glow of the Big Bang, astronomers can test inflationary models and examine the early conditions of the universe. The precise measurements of the CMB from JWST will provide vital data to refine cosmological parameters and enhance our understanding of the universe's origins and evolution. Although the lambda CDM model provides a solid framework for understanding the large-scale structure and evolution of the universe, ongoing observations and theoretical challenges are pushing scientists to refine and expand our cosmological theories. The launch of JWST represents a groundbreaking moment in cosmology, offering unparalleled opportunities to explore the universe with unprecedented sensitivity and resolution. As JWST continues to reveal the hidden secrets of the cosmos, it promises to transform our understanding of the universe's history and inspire new generations of astronomers to push the boundaries of human knowledge. Gas accumulation onto cosmic objects has a natural limit, as material can only accumulate at a certain rate. While specific physical conditions can temporarily push an object beyond this limit, sustaining such a process over long periods is not feasible. In fact, only about 10% of gas typically turns into stars in galaxies. For galaxies to form at the rapid rate and size observed, nearly 100% of the available gas would need to be converted into stars. While 100% conversion is theoretically possible at the edge of what is allowed, it would require something fundamentally different from what we currently understand. Some individuals argue that our standard cosmological model could be entirely wrong, even suggesting we should abandon the Big Bang theory as an explanation for the universe's origin. They propose alternative explanations, such as new laws of physics, a form of early dark energy, or that the universe may have formed with exceptionally large black holes or even exotic matter like a new type of particle that decays into normal matter much later in the universe's history. While many dismiss these ideas as far-fetched, it's important to note that before the official launch of the James Webb Space Telescope, various problems had already emerged with our current understanding of cosmology. One major issue is the nature of dark matter. In the lambda CDM model, dark matter is hypothesized based on its gravitational effects on visible matter and the cosmic microwave background, but it has never been directly detected. Despite extensive searches using various detection methods, including direct detection experiments and indirect observations of galaxies, the exact nature of dark matter remains unidentified. Another problem lies with dark energy and the cosmological constant. The introduction of the cosmological constant, lambda, was initially proposed by Einstein but later discarded. It was reintroduced in the late 1990s to explain the accelerated expansion of the universe, but it presents challenges when trying to reconcile the tiny value predicted by quantum field theory with the observed energy density of dark energy, leading to what's known as the cosmological constant problem. Furthermore, simulations of the universe's structure formation also face challenges. While the Lambda CDM model successfully predicts large-scale structures and the distribution of galaxies, discrepancies arise at smaller scales. Simulations often overpredict the number of small satellite galaxies around larger ones, like our Milky Way. This missing satellite problem suggests that either our understanding of dark matter is incomplete or that the simulations need additional refinement, possibly incorporating more accurate physics for standard matter. In conclusion, the Lambda CDM model, while successful in many respects, faces several unresolved issues, especially when trying to explain smaller-scale cosmic structures and the elusive nature of dark matter and dark energy.